Good evening, everyone. On behalf of the European Shoulder and Elbow Society, I welcome you all to our first collaborative webinar with the International Shoulder Group Society of Biomechanics. My name is Jagwant Singh. I am the chair of the Healthcare Delivery Committee of the European Shoulder and Elbow Society. I would like to thank my co-chair, Dr. Martin Warner from University of Southampton. He has been instrumental in setting up this collaborative webinar. So the webinar is in two sessions. The first session is 4 talks, and then we'll have the question and answers at the end of the session, followed by the second session. We're grateful to our speakers. They don't need an introduction. They are quite renowned in their fields, and we're honored to have them here this evening, and we really appreciate their time and their commitment to make this happen. We have Dr. Joaquin Sanchez-Sotelo. He's the division chair of the shoulder and elbow surgery at the Mayo Clinic. He's quite well published with more than 450 articles and over 50 book chapters. He co-directs numerous courses, and he is the president of the American Shoulder and Elbow Society. He has special interests in shoulder reconstruction and also biomechanics of the shoulder and elbow injuries and implants. So we are pleased to have him here. Our second speaker is Tjarco Alta. Uh, I have been his colleague, and we work together in the healthcare delivery committee of the Shoulder and Elbow Society, and he was instrumental in setting up this webinar and the collaborative work. He is at present the president of the Dutch Shoulder and Elbow Society, and also the Congress president for the 2025 SECEC Congress at Rotterdam. Our third speaker tonight is Professor Puneet Monga. Professor Monga is based at Wrightington, United Kingdom, and he is heavily invested in research, teaching, and training. His research interests are in glenoid reconstruction and arthritis in younger patients. He also is an innovator, and he's been working on 3D printing jigs and also designing implants. So we're pleased to have him here. Professor Philipp Moroder is based in Zurich. He has an illustrious CV with publications more than 180, and he has numerous awards to his name, including the Charles Neer Award and the Hawkins Award, and also the Cremont Award. So we welcome him here on the webinar. Before I hand over to my colleague, Dr. Warner, I would like to thank my other moderators. We have Ruth Delaney from Ireland, Solane Gain from France, and Bart Jan from Netherlands. I really appreciate your time and your commitment behind this. Thank you. Over to Dr. Warner.
Thank you for the introduction there, Jagwant. From the International Shoulder Group, I'm very pleased to welcome two very well-established researchers in the field of shoulder biomechanics, and really glad to have this joint collaboration between ourselves and the European Shoulder Society. Jagwant, if you go to the next slide. So I'd like to introduce Professor Anthony Bull. He's a professor in musculoskeletal mechanics at Imperial College London. Anthony's research is focused on the basic mechanics of joints and the application of this knowledge to support development of new technologies to support the diagnosis and treatment of musculoskeletal pathology. Specifically, Anthony's work involves the development of orthopedic implants and surgical design across the lower and upper limb biomechanics and in aging. Next slide then, please, Jagwant. And I'd like to very very pleased to introduce Professor Laurie Michener. She's the Director of Clinical Biomechanics and Orthopedic Outcomes Research Laboratory at the University of Southern California. The central theme of Laurie's work is around defining optimal treatment pathways for patients with musculoskeletal shoulder disorders by focusing on characterizing the mechanisms and defining classification and management approaches to define optimal outcomes of care. So that's our speakers from the International Shoulder Group, and really pleased that we have this joint collaboration between our respective groups.
And just for the certain housekeeping rules for our participants, the Q&A box is there for the questions. The recordings for this webinar will be available on the SECEC YouTube channel. And if you have any feedback, please send it to our secretariat, and it'll help us to improve our future webinars. Thank you. We can have our first speaker, Dr. Joaquin Sanchez-Sotelo.
Good evening, and thank you very much for the invitation to participate in this fantastic webinar. I just love this idea of getting surgeons and experts in biomechanics together, because sometimes we surgeons don't fully understand the biomechanical principles, and sometimes experts in biomechanics don't have the chance to know where is it that surgeons are going with our shoulder arthroplasty techniques and implants. So tonight my task is to discuss over the next 15 minutes what are we doing today as surgeons on the humeral side when we do a shoulder arthroplasty. These are my disclosures, and they are relevant because I helped Stryker design the implant that you will be seeing in most of these x-rays. So of course there is a conflict of interest that is almost impossible to avoid when we talk about implant design. It's interesting to reflect about how the humeral component has evolved over time, and when the history of shoulder arthroplasty started, at least in North America with Dr. Neer as the father of shoulder arthroplasty, all we had was a very long, 15 centimeters, always cemented, monoblock humeral component. And if we now think about where we are today, we have gone through a number of waves of evolution, including going cementless, having the possibility to use a modular component where the humeral head is separate from the stem, making it adaptable to different versions and angles, having fracture-specific stems. Then, of course, the revolution of reverse shoulder arthroplasty, and more recently, the possible application of stemless to the field of reverse prosthesis. When surgeons talk about what is it that they would like to see when they implant a humeral component, most surgeons in 2025 agree upon the following. We want to have a family of implants where with the same implant you can go anatomic, reverse, stemless, short stem. We also prefer cementless fixation for the most part, although I believe that cemented should always be optional for patients with low bone mineral density or maybe fracture applications. On the anatomic side, we really want to get the humeral head biomechanically and anatomically well reconstructed, which was a problem in the past, as we will discuss. On the reverse application, most surgeons are moving on to a more vertical or varus polyethylene angle. We desire to have high performance polyethylene and an adequate capture ratio. And finally, we want to avoid two problems we have seen come up to the surface with short stems, including stress shielding and poor alignment. What problems have we faced in the past on the humeral side? Number one, there was a time where modular cementless prosthesis did not allow surgeons to get the head where we wanted. And oftentimes the head was too high or too large, and that would edge load the glenoid component and lead to loosening or strain the rotator cuff. Number two, when we migrated to shorter stems, this has a major implication on the opening angle of the reverse arthroplasty. For example, if you choose an angle of 135, but the component is placed in severe varus, all of a sudden your true opening angle is 125, and that increases the dislocation risk. By the same token, if we place the implant in too much valgus, now we're almost approaching 155 or Gramonte style, which we know will create notching. Number three, not using a platform prosthesis can be a problem. You can see on the X-ray on your right, a patient with a very well fixed, long, cementless humeral component, and almost no tuberosity because of stress shielding, you can imagine how removing that implant is going to be danger for the humerus. It's way better to use platform systems so you can revise the glenoid component to a different design, but they still maintain the humeral component because it's a platform prosthesis. So we want to avoid the use of long, non-platform stems. If we use cemented fixation, use restrictors so that the cement doesn't go all the way to the elbow, and in the revision setting, retain a platform prosthesis whenever possible, which may require to combine different manufacturers. And finally, a problem that was not really brought up to the attention of everyone until Dr. Rice published a landmark paper with Dr. Walsh, where he showed that one component, and this is a different one, over time will lead to stress shielding. As you can see, there is a massive amount of bone loss proximally in the calcar and the tuberosity because as we went shorter with the stems, we also went wider. And you get to a very large fill-fit ratio that will completely change how the bone reacts to Wolff's law, because when there is no metaphysis loading and the implant is very large, stress shielding will occur. So the design principles of contemporary shoulder arthroplasty revolve around two concepts. One is that we want to go shorter and shorter and shorter. So now most surgeons favor use of a short stem or a stemless prosthesis. And in the field of reverse arthroplasty, glenoid lateralization is king, meaning that most surgeons do like to lateralize using either a bone graft with bio-RSA, a large sphere like the Mark Frankel's philosophy, or a metallic wedge, as you can see on the image on your right. So what we desire to have today is this family of implants where with the same component, you can go from a stemless to short stem to long stem, from anatomic to reverse, and you have this flexibility intra-op, but also the possibility to convert post-operatively. Because we lateralize so much on the glenosphere side now, we have to make sure that our polyethylene is actually at the cut surface at a minimum, because otherwise the overall joint tension is too much. Third, we want to minimize stress shielding by loading the metaphysis. And number four, we have to still be able to reconstruct the humeral head anatomically. So how do we get there? Some implants and some companies are designing prostheses where the preparation of the metaphysis is identical. If you use a stemless prosthesis, a short stem, a standard stem, a long stem, or a fracture stem. And that helps because if you prepare for a stemless prosthesis and you don't get fixation, or you want to change to a reverse where you may not trust fully a stemless configuration, you can just easily drop the stem and nothing changes. And this idea of expanding fixation to the periphery hopefully is going to help us. Why? Because if you look at the cross-section of a humeral head, as you can see, the center of the neck, right here where we place our fixation device, is actually almost empty of bone, especially in patients with osteopenia, whereas the periphery is where the bone really is. So trying to maximize fixation requires to go to the periphery, but that also helps to minimize stress shielding because now the stress is going all the way from the top around the metaphysis and into the humerus. Having a family of implants allows some flexibility. So if you're doing a stemless and you are unhappy with the fixation, you can quick convert to a stem. Or if you all of a sudden realize that you need to do a reverse because of poor tracking of the humeral joint or calf disease, then you will do a reverse prosthesis. And this also allows convertibility where if the patient has a reason for revision, for example, calf failure or subscapularis failure, we can just remove the humeral head, place a polyethylene reverse bearing, and basically convert an anatomic to a reverse arthroplasty. However, because the stem sometimes will dictate where is it that the metaphysis portion of the stem is going to land, you need to have a collection of different head diameters, thicknesses, and couplers so that you can really anatomically reconstruct the humeral head in the anatomic application. We also know through the joint registry in New Zealand and Australia that at least in anatomic arthroplasty, modern polyethylene like vitamin E polyethylene or hylicrosine polyethylene is beneficial. And of course, every system will have a number of options just in case you want to adapt to a more varus or more valgus angle of your poly and the different thicknesses. And something that I myself was not familiar with is that every manufacturer will choose randomly what we call the capture ratio, which means how much of the polyethylene is actually around the sphere. And some companies will have all the way to 35% or 45%. Some will have all the way to 65%. Of course, the smaller the capture ratio, you can imagine how there is less impingement, so that increases mobility, but also increases instability. Whereas the thicker capture ratio with a 65% capture will give you more stability, but maybe also more impingement. And this is a table that shows where is it that just a few manufacturers land, and you can see how it's all over the board. So as we move into 2025 and forward, I think we surgeons have to understand the biomechanical aspects of this capture ratio that until now was, for the most part, ignored. So in an anatomic application, even though most of us favor today a stemless prosthesis, number one, you have to be ready to change to a stem if necessary. And number two, alignment is very important, because if you get the implant malaligned, it is likely that the mechanics of the shoulder will just not be perfect on either an anatomic or a reverse application. For that reason, I prefer to use an IM cutting guide as a reference until we have PSI guides for the humerus, like some companies offer, or maybe navigation, or maybe robotics. But this way, you know for sure that the stemless or short stem alignment is going to be helped at least a little bit by the location of your axis. And of course, to be anatomic in an anatomic application, you want to make sure that your humeral cut is exactly flush with the insertion of the supraspinatus into the greater tuberosity. And as we all know, there is a bare area at the infraspinatus insertion, and that will leave a little bit of rim that you can use to guide the position of the humeral head. And one thing that I think has become extremely beneficial when we do a stemless anatomic shoulder arthroplasty is that now you can remove the humeral head. You can understand where is it that the osteophytes mark the true outline of the humerus as it was before the joint became arthritic, and you can use a humeral head trial to make sure that you're going to be anatomic, yes or yes. This was not possible with long cementless stems of the older generations because they dictated where the humeral head lands, whereas now you can actually get the component exactly where you wish, and then all we're going to do is size for the metaphysis and go ahead and rim proximally, place our humeral component, and then we can trial with different head diameters and thicknesses and make sure we get the humeral head truly anatomic. And the reverse application becomes similar. So after one has done our preparation, in this case, we're using a stem prosthesis, and then it's a matter of choosing your implant of choice. And I think most surgeons, as I talked about, from a mechanical perspective, are migrating to a 135 angle with a capture ratio of at least 50 or 55%. And then the thickness, of course, is based on soft tissue tension. So in summary, I think it's important to realize that if we go back to the 50s and 60s and 70s in North America, where all we had was the near long stem cemented monoblock, and we think about today where we have a stemless, shorter stems, anatomic, and reverse, there's been a major improvement in design. And I think now we're likely to have these contemporary platform systems that are optimized both for anatomic and reverse arthroplasty. Thank you very much for your attention.
Thank you, Joaquin. Really interesting. So, Marie, can we present the second talk, which is from Tjarco, Alta?
Hello, everyone. My name is Tjarco, Alta from the Netherlands. I'm having the flu at the moment, so sounding a bit nasally, but hopefully you can understand and hear what I'm saying. First of all, I would like to congratulate Jagwant and Martin for putting together this wonderful webinar with this collaboration between engineers and, in this case, shoulder surgeons. Hopefully there's more collaboration to come. We're going to talk about stemless reverse shoulder arthroplasty. Where are we at the moment? This is my disclosure. I'm a consultant for Lima, but I'll try to be objective as possible. If you look at the literature, this is the first system from the test that has the longest follow-up. These are slides from which I got from Philipp showing good results at mean of 129 months follow-up. However, the test is not longer on the market. Another system which is already very long out there, this is the Verso system from Orfo-Levy. We hear some slides which I got from him as well. And if you look at more broader literature in a systematic review, and then they're all saying short-term outcome stemless reverse is the same as stemmed reverse. However, as this is also showing a higher revision rate in the beginning, so proceed with caution. This is from the group from Claudio Rosso, showing the results, similar results as we are finding with the same system. In the beginning, good result with the reverse. Not being dictated by the stem can also provide an opportunity, because the graded tuberosity osteotomy in fracture sequelae, as we heard from Pascal Boileau, is related to poorer clinical outcomes. So if you can leave the tuberosities where they are and put the implant in a more varus deformity, as you can see here, not being dictated by the stem, you can still have a nice option for fracture sequelae. This is a valgus deformity, 79-year-old lady with her MRI, and this is her 4.5 months post-op X-ray, and hopefully she'll be coming shortly for her 1-year follow-up. Another example for a failed graded tuberosity repair in 2017. This was the same situation in 2020, and she came to me in 2023 with her situation. Graded tubercle, all displaced, external leg signs. So I decided also to do the tendon transfer combined with the prosthesis. But the advantage of not having the stem in there is that you can place your drill holes to fix the tendon transfer at any position you like with no stem in there. Here another case, osteoarthritis in 2017, and then sustained a fall with a fracture, which was healed in even further bowing. It was a case from Marco from the Pluim in the Maart's clinic, so I went over there and we did it together. And this is his 1-year post-op situation. Very happy. I wanted to show you this because in younger patients, if you need to do a bio-RSA, for instance, then you can still harvest the bone from the humeral head, like you're doing most of the time with a donut. And then this is the situation after that, and it's still good bone quality and good bone enough to have your core fixated in the metaphyseal area. Here's a case from our group. Retroversion of the glenoid of 49 degrees, type C glenoid, and this is the 1-year post-op result in growth of the bone graft. Periprosthetic fractures can be a problem, like you see here. 66-year-old lady, long stem, a normal stem reverse, had another fall, so she needed to be revised to an even longer stem. So that's a lot of metal in your shoulder for a 66-year-old. So hopefully in the future, this is the first case report of non-operative treatment of a humeral, of a humerus with a periprosthetic fracture after a stemless anatomical prosthesis. Not yet described for stemless reverse, but who knows, that might come. I'm struggling still with the neck shaft angles, which are not dictated by the stem, so you need to do a freehand cut. The Lima insert is 7 degrees, so it corrects 7 degrees. So probably I should have made my cut here, because now I ended up with a neck shaft angle of 152 degrees in the right, on the right. So not being dictated by the stem is also having not very consistent neck shaft angles. The other thing which I'm still struggling with is the ingrowth of the tubercular titanium core in the metaphyseal area. This is a male, 75-year-old. This is where the humeral cut was done. Here you're not seeing it maybe so clearly at 4 months, but at 1 year you're seeing it very clearly. The humeral core tilted into varus, and I've got now 2 cases of those. So the ingrowth of the core within the first 3 months is not completely stable within those first 3 months. This can also happen the next day, completely tilted out. So that was revised to a stem the next day, and this is cases from myself. I was still hoping that it was only dislocated, but the fact that the prosthesis is lying on my desk here meant it was loose. And it was not a very difficult revision to stem the next day. However, you don't want that for your patients, obviously. So looking at bone quality in the metaphyseal area, we're now using this study from the Bernard Jost, looking at the distal tuberosity index. And if it's greater than 1.4, it's supposed to be good bone in the proximal humerus. Another instrument which can be very helpful are the Hounsfield units. Everything above 0 is good bone quality. So we're now getting from our radiologist the Hounsfield units at the level of the anatomical neck. Another trick which I learned, which I'm now doing, is that I'm measuring the right size and the right depth, and then I impact and ream one size smaller than the core I intend to place. In that way, having a press fit of the definitive core, basically like the acetabular component which is placed by a total hip, like our hip colleagues are doing. This was recent from the group from George Abwell. They had a finette element analysis looking at all the different neck shaft angles. And the interesting thing they found is that if you have a neck shaft angle of 130, then you have a bigger chance that the implant will be loose. And they advise to have a higher neck shaft angle because that could have better humeral component stability. So coming back to the slide I showed you before, and looking at the TESS system, the 145 degrees mean neck shaft angle is behind my head, but that's what they found in the study I showed you. And the Verso, they are having an initial cut of 155, and then the liner corrects to 145. So what I end up now doing is more cutting under 145 neck shaft angle and ending up with a neck shaft angle around 150 degrees. For the discussion, this is from the Australian registry. Stemless anatomical prostheses are very promising, and I know stemless reverse is not the same as stemless anatomical, and we still need to look at the humeral side. However, maybe this is the future. So in summary, short stems, stemless reverse is the same as stamped reverse. Not being dictated by the stem provides opportunities, especially in post-traumatic cases. Neck shaft angles are not very consistent. Ingrowth of the core in the first 3 months is less stable, and it also depends on the bone quality. Distal tuberosity index and the Hounsfield units can help you preoperatively decide if you want to do a stemless, yes or no. Better core instability, ream and impact one size smaller. And another, which is now interesting, is strive for 145, 155 neck shaft angles, because then there's probably better core stability as well. However, long-term follow-up is needed, especially on the humeral side. Thank you very much, and see you all in September in Rotterdam. Bye.
Thank you very much to Tjarco. And now for the next speaker, Professor Monga from Wrightington is going to take us through an update on glenoid component in reverse shoulder arthroplasty. Thanks, Puneet.
Good evening, everyone. Firstly, thank you to the SECEC committee, to Jagwant, Martin, Ruth, to the moderators. Thank you for putting up such a nice webinar. So it's a big topic to cover the glenoids. Here are my colleagues from Wrightington, and I cannot start a talk like this without paying tribute to Sir John Charnley. I work in this wonderful place, which is the birthplace of the modern hip replacement. So there's no end of inspiration from my predecessors and lovely colleagues. These are my disclaimers, but I'll try and keep my talk away from my conflicts. The glenoid, well, that's the challenge in the shoulder and has been a challenge for a long time. And we learned a lot from the hip surgeons. The hip itself is a deep socket. It is part of a big bone, the pelvis, and it's attached to a very stable base. Whereas in the scapula, it's completely the other way around. It's small, it's shallow. It doesn't have a stable bony articulation, and you have to approach this glenoid from the front, and it's located at the back. So we already have a challenge. When we talk about the glenoid, I thought I'll talk to you all about the biomechanics from the point of view of a surgeon. And as I understand it, there are three types of movements happening in the normal glenohumeral joint. There's a beautiful rotatory movement with the center of rotation in the humeral head, with the ball spinning on its central axis, on the central pivot point. There's the sliding movement, almost like a shear, like a sledge going downhill. And there's the rocking horse movement, where you have almost like a car wheel rolling on a road. So the rotatory movement is very nice. It's smooth. You can give lubrication and the joint can work very nicely like a hip replacement. But the sliding and rolling movements are a problem. And we'll see how that affects the glenoid. Central to that function is the role of the rotator cuff. So in a normal glenohumeral joint, you have a rotator cuff which gives compressile force, and it is really optimizing for a rotatory movement over a sliding and a rocking movement. So when shoulder arthroplasty started, really we were doing hemiarthroplasties. But the trouble with hemiarthroplasty, of course, is that we haven't replaced the glenoid. So there was a risk, and there still is a risk, that the patient comes back with glenoid pain. So if you look at the joint registries and the data from various studies, it proves that, yes, there is decent survivorship, but we run the risk of having persistent pain from the glenoid. So if you look at the picture on the right, here we have a slightly happier glenoid, and there's been a lot of work done on softer materials like pyrocarbon. They're softer on bone. They're supposed to be preserving the glenoid bone. And they also have a biological property which actually aggregates phospholipid on the surface, so which will add to a more optimal function and less erosive on the glenoid. There's still work to be done, but the initial data coming out of registries is very promising. So that's where we are with hemis. Now, obviously, as technology progressed, we moved on to anatomical total shoulder replacement. And the initial designs were conforming designs, which means that the radius of curvature of the humeral head and the radius of curvature of the glenoid articular surface was similar. Now, that of course allows rotatory movements, but it prevents rocking and sliding movement. And that can then lead on to loosening. So most modern anatomical joint replacement will have a non-conforming design, which allow a degree of sliding and rocking movement. And again, we'll see how that comes to play when we talk about modes of failure. So generally a 4 to 10 millimeter mismatch of radius of curvature is optimal. And that's something which is built into most modern systems. Now let's talk about the modes of failure for anatomical replacement. Most studies have shown that the common mode of failure is cuff failure. Cuff fails, and the rotator cuff then cannot provide the centering force which allows a rotatory movement. And if you look at the pictures in the middle, you can see a sliding movement at the top or a rocking movement. What that does, it leads to delamination or eccentric wear of the poly, and then we start to see loosening of the glenoid at its base. So the glenoid bone interface becomes loose because of this abnormal mobility. So when we had problems with that, we went back to the engineers and said, well, we have a problem with glenoid fixation. So they came up with this metal back fixation. What the metal back fixation does, it improves the bonding between the glenoid and the bone, but the downside of that is that the poly becomes thinner. And sometimes, if you're not careful, if the component is very thick, you can have too much stretch on the rotator cuff. So when we start to have abnormal mobility, like the rocking and the sliding movement, all the stress is taken between the humeral head and the metal component. So then we start to see component fractures, screw breakages, component dislocations, and metal wear. And really, there's been studies showing that conventional metal back glenoid components do have a high failure rate. So we haven't solved the problem. So we go back to the engineers. And that's where we are. There are some glenoids available now with a hybrid form of fixation, either with a hybrid between cement and metal, or just a surface of metal at the back of the glenoid component, which will then allow a thicker poly to be placed. Now, this will obviously these are early designs, and early results are very promising. but I think we need to wait for the medium and long-term studies to see if that actually helps in longevity of this implant. So that's where we are with the anatomical replacement. The significant challenges faced in patients with B2 glenoids, and really you can take your pick. At this stage for a B2 glenoid, because the humeral head is off-centered, the cuff is dysfunction in one place and stretched out in another, we could use a hemiarthroplasty, and you can speak to different surgeons and they come up with a different answer. So hemiarthroplasty with high-sided reaming, pyrocarbon head, anatomical shoulder replacement with a standard component and high-sided reaming. My personal preferred option is an augmented component. We have a massive population of rugby players up north, and they have, in these young patients, we do have B2 glenoids, and we see that so often. So the advantage of a built-up polycomponent is that it allows restoration of the joint line and correction of subluxation. And again, these are really challenging cases, and I think there is more evidence needed, more research needed, how we deal with this in the long term. Now, we are obviously finding it a challenge to deal with the glenoid in the anatomical setting, but then comes reverse and changes the game. So when you place a glenosphere on the glenoid side, suddenly you've converted 3 movements into one relatively simple movement. So now we're almost talking like a hip surgeon, where you have a relatively simpler movement. So even in the absence of rotator cuff, we can convert our joint geometry into simpler reconstruction. So when Paul Grammont came up with this beautiful design of medialization of the center of rotation and distalization of the humerus, we were leveraging the deltoid force. And obviously in the last 10 to 20 years, it's become so popular. And part of the reason why it's become so popular is that the biomechanics of the glenosphere humeral liner interface is a simpler movement. It helps, of course, that the deltoid force is optimized. So the two functions of two components of a successful reverse shoulder arthroplasty is to minimize any bony impingement for a better range of motion and optimizing the deltoid function. And of course, we'll hear from Philipp about the scapulothoracic mobility and the posture as well later on. When we talk about the base plate configurations, there are a vast variety of choices. You can use pegs, screws, monoblocks, modulars, different shapes of the base plates, number of screws, wedges, and really it is possible to reconstruct any glenoid. We have a vast experience of over 220 to 230 custom joint replacements now in our unit, and you can build up what you want, really. So the deformity is no longer an issue for almost all cases. So I think, again, we've been tremendously helped by our engineering colleagues. And I think one thing which has been fascinating when you look at the biomechanics of the deltoid specifically in a reverse is, if you look at the picture on the top left, this is a classic Grammont style prosthesis with medial center rotation, 155 neck cut. And if you look at the deltoid force, it's relatively vertical. And if you go back to high school physics and resolve that vector, as you see on the top right, you have a vertical component and a horizontal component of that deltoid vector. And you can see in a Grammont style prosthesis, the relative size of the horizontal vector is small. But when we come down to the next picture on the bottom left, we've actually added a metal or a bone offset beneath the base plate. And by doing that, we're lateralizing the center of rotation, lateralizing the whole construct on the humeral side, effectively moving the deltoid in a little bit more oblique position. And what it does, it improves the medial component of the deltoid vector. What it's doing is improving the deltoid wrap. So the more medial force we have, the better deltoid wrap we get, the more stability we get, the optimal the force is. And that's why glenoid lateralization, or lateralizing the center of rotation glenoid, has become very popular and most important. Of course, Joaquin has already covered on the humeral stem, and I'll just like to say it's an extension of the same philosophy, whereas as you go from 155 neck cut, and picture on the top left, to the 135 neck cut, you're actually making the deltoid vector even more horizontal, more oblique, and it actually helps in a compressile force, improving function and better range of motion. Now, the challenge we face in terms of biomechanics of lateralization and distalization is, number one, how to measure it. I don't think there is agreement yet on how to measure it. Although these beautiful angles have been demonstrated, there is controversy. And if we know how to measure it, what are the values? I think that's where we need to work on over the next many years. There's been a huge amount of improvement in our surgical quality by using these online planning software. This is a picture of the blueprint, and the understanding and the teaching and the training of our fellows has improved tremendously by using this software. And of course, we have some idea of where to place these base plates on the glenoid side, but there's still more work needs to be done in terms of interplay of these factors. So for example, you could say the base plate has to be inferior, but does it have to be really that inferior if you lateralize it a little bit more? Can you go a little bit higher and lateralize it? Would that affect impingement? Would that improve our outcomes? So there's a lot of work to be done once we start using these tools. Again, that's thanks to the engineering colleagues. And then once you plan it, you can go to the engineers and say, can you design a guide? We can either have customized guides or intraoperative imaging with a GPS system. Again, that's really useful. And I think moving on to customize implants, that's been a game changer for some of the cases that we see where we would otherwise have told them to go away and offered a simpler solution, but here we are able to offer a much better fixation on the glenoid with customizable base plates. And again, the results we are seeing with these kind of implants is tremendous. So we've gone from a place of hemi-arthroplasty all the way onto a customized reverse shoulder replacement. And I think there's still a lot of improvements to be done. But this is a picture from the UK National Joint Registry. We have over 70,000 patients on the registry now. And it's really nice. You can see the best performing arthroplasty, which you can see the line at the bottom of the graph. And it's the reverse. A stemmed standard reverse offers a survivorship of nearly 96% at 11 years. And the worst one, and it's not right to say worse, because even a hemi-arthroplasty is taking you up to 90% survivorship at 11 years. And I appreciate there are limitations of registry data, but that's not bad. And I think we're heading in the right direction with this. So I think we made a huge amount of progress. I've touched upon various challenges that we face on the glenoid side. And I think the future is going to be very exciting for this.
Thank you, Puneet. Awesome talk. And Marie, can you put the next talk from Anthony?
Well, hello, everybody. It's my great delight to have been invited to present some work on reverse shoulder arthroplasty. This is work done with my colleagues and collaborators and PhD student Andra, my colleagues Ulrich, Peter Riney and Toby Baring, and we're all based at Imperial College London. I'm going to focus on the reverse, and the reason for this, I think, is obvious to many people. The first is that the distribution of primary shoulder procedures, the proportions that are reverse shoulders have just rocketed up, and of course the numbers are increasing anyway as well. The numbers of hemi-arthroplasties and of anatomical total shoulder arthroplasties are reducing proportionally. And of course, there's a lot of interest in how these are doing, and there's a lot of interest in the biomechanics of these as well. And of course, that's the context of our work, and the context is also that we're interested in scapular fractures. It's obvious to us all when we look at these images, these cartoons that we've created of the different types of shoulder arthroplasty, that there are fundamental differences between them all. But why have we ended up with the reverse? Well, there are many reasons. One of the things is that we know that the outcomes now are very good. Compared to the preoperative state, patients have an improved range of motion. Of course, it's not the healthy range of motion, it's still pathological in many ways, and it can be tuned and modified, and that's something I'll mention a little bit later. Patients demonstrate improved strength, a reduced amount of pain, and good patient-reported outcomes that are improved significantly. So as such, it's become a popular procedure. But obviously, many more people are now having it, and so there are many more issues that arise. I'd just like to mention a little bit this key point of the center of rotation, highlighted in lime green, and also deltoid length. So the deltoid length is shown by these orange lines. And these orange lines obviously show that after the reverse shoulder arthroplasty, the deltoid has lengthened. Therefore, it's now functioning in its different length-velocity relationship, and that changes its function. The center of rotation has also moved from about here to, on the right-hand side, to maybe a little bit inferior and maybe more medialized, but not in all cases. What does this do? This increases the moment arm of the deltoid, the distance the deltoid is away from the center of rotation of the joint. And as the moment arm is increased, force times moment arm is moment, and moment is what you need to elevate your arm, and therefore the forces in the deltoid reduce. But what if we were to change this and lateralize the reverse shoulder? Why would we choose to do that? Well, when we have a medialized shoulder, we get this problem of the range of motion is severely inhibited. When we lateralize it, we can increase the range of motion, significantly increase the range of motion. What happens is, though, the moment arm of the deltoid is now reduced, and therefore to introduce the same torque, the same moment that lifts the arm up, then you have to increase the forces in the deltoid. And so you have this trade-off. And if we think in terms of simple mechanics, the sort of the lever arm effect of the force times the distance, well, it's an optimization between them. You increase the distance, you can reduce the force, and vice versa, like on a seesaw. Focusing on this reverse arthroplasty, these are the clinical problems that are seen. You get this impingement, which starts notching, chewing away the scapula underneath the glenoid. The glenoid component itself can loosen and get failure. In some cases, some instability, although primarily this is a very stable joint replacement. And the deltoid has stretched. And so you get in some cases, this deltoid problem where its integrity is lost. The main focus of this presentation is scapular fractures, which in some papers have an incidence of over 10%, but I think it's accepted now that incidence nowadays is between 3 to 5%. And the risk factors are fairly straightforward. The female sex, low bone mineral density, thinner scapulae. And there are some studies that teach us that if you lateralize the glenoid component, then you increase the strain on the scapula and on the acromion, which could be related to failure. If you push it down, then you reduce the strain. But if you lateralize the humeral component, it's not quite clear what happens. Anyway, we're going to focus on the glenoid component only here. And typically, if we use these Levy zones, then this paper from Crosby, Hamilton, and Twiss show that mainly types 1 and 2 occur, type 3 doesn't occur quite so often. So we come back to this point where we can move around the glenosphere position and change the momentum. We can move around the humeral component as well and change the momentum. But what does acromioplasty do in this? Well, what is acromioplasty? For those who don't know, acromioplasty is where you chew the end of the acromion here surgically, and what that does is it changes the way the deltoid wraps around from this red line to this lime green line, you change the moment arm a little bit, but also you change the direction of the load application on the acromion. So if we think now of our lever arm effect here, the green is the center of rotation, D is the deltoid force, L is the length. Let's simulate the wrapping around the acromion. This is the red line. We then chew away part of the acromion, and the deltoid pulls in a slightly different direction and with a smaller moment arm from the center of rotation, resulting in potentially a higher force. But of course, it does change what's happening further back on the scapular spine. And so this is this optimization that we're trying to understand. And so the approach that we have taken is to end up with a computational model that allows us to investigate what happens. But rolling back from that, we start with understanding what the forces are on the scapula. We use computational musculoskeletal models from that based on lots of in vivo experiments for activities of daily living. They provide us with the forces. They provide us with an understanding of what forces we can apply on our computational models. Prior to all of that, we need to do some direct measurement. And so what we did is we established a cadaver model where we were able to mount the scapula in a consistent way. We were able to implement strain gauges on the scapula, and those strain gauges were positioned on the 3 zones, where zones 1 and 2 are the ones that have most highest incidence of fractures compared to zone 3. And that allows us now to directly measure what is happening in those locations. But how do we apply loading on the deltoid? And this required a little bit of experimental work. So one could dissect the humeral insertion of the deltoid, wrap the deltoid with cloth, which we've done previously, and then pull on the deltoid. But the forces that you can apply are not very high. And so what we wanted to do was maintain the insertion on the humerus and be able to pull on the humerus. But of course, if one were to do that, then one would be dislocating the humeral head. So what we did was we cut the humerus, and then we put a telescopic rod between so that we could pull the distal end of the humerus, which pulls the deltoid insertion, which allows us to load to very high forces, but maintain the anatomical position of the humeral head. And so this is our experimental apparatus. Our experimental apparatus allows us to mount the scapula and the shoulder. It allows us to raise the position of the humerus to any angle of elevation along this rail. And we can change the orientation of the scapula so that we can elevate the humerus in abduction, scaption, or forward flexion. Of course, we then also need to implement our surgery. So we conducted our surgical implantation of the glenosphere. And of course, we could chew away the acromion and do the acromioplasty. And we did this in a very consistent way, measuring everything that we did so that we were sure that we were consistent between specimens. So we have 3 conditions of the shoulder. We have native shoulder, we have reverse shoulder arthroplasty, and we have reverse shoulder arthroplasty plus acromioplasty. We have adduction, scaption, forward flexion, and we loaded up to 150 newtons. Here I'm just going to present the 150 newtons. We started with 8 specimens, but 1 failed before we got to 150 newtons, so we're unable to present those results. I think demonstrating that 150 really was the maximum you could get to. The elevation angle along the bottom demonstrates glenohumeral, or humeral elevation relative to the scapula, and not humerothoracic elevation. So these numbers are obviously much higher in humerothoracic. So really we're going up quite high, and we're capturing really the normal range of motion And as expected, we have higher strains in zone 1 and 2 than in zone 3. This is in abduction. These are normalized strains, normalized to the maximum that we measured for that specimen, for any of the tasks. Scaption. So now we're moving from abduction forward to scaption, and we have a higher strains, and not just in the low angles of elevation, but slightly higher angles of elevation as well. Higher strains for all, but the highest now in zone 1. And forward flexion maintains that trend. So what happens when we do the surgery? So what we're looking at here now is the position of highest strains on the scapula, which is forward flexion, where blue is the native shoulder, red is arthroplasty, and then green is with acromioplasty afterwards. And we find that at the higher angles of elevation, in particular, the acromioplasty reduces the strain in zones 1 and zones 2, not in zone 3, but the strains there are low anyway. This is not consistent and it's not statistically significant, but of course that doesn't mean that it's not significant for one of those specimens, or in fact most of those specimens. So perhaps this highlights for us that this surgery is complicated. It might have a beneficial effect, the acromioplasty, but it's not consistent between specimens. So then this moves us towards our computational finite element analysis. What we want to do is we want to have a tool where we can test pre-surgically what the outcome of the surgery might be, whether or not medialization or lateralization is appropriate for this patient, whether or not an acromioplasty is required, and any other anatomical or considerations that we need to make. So what we did was we set up models for the same specimens that we had the physical experiments for. We focused on replicating the experimental condition first before we could then creatively do other loadings and apply other muscle forces. We discretized the deltoid into 50 elements. We recognized that when you pull on these elements, they can wrap around the humeral head in a non-physiological way, so we had to connect the long fibers of those deltoids together with perpendicular springs, and that then allowed us a very sort of physiological wrapping of the deltoids, and we could replicate the loading that we did in the lab. And by overlaying the three-dimensional computational models with the photographs of the position of the strain gauges that we had in the lab, we could verify the strains that we were getting computationally with the experimental strains that we measured on each specimen. All strains have a direction, and so we could use the strain transformation equations to do our validation. And what our results are showing is that the trends are all consistent. They're all the same between the computational models and the physical models. We have done this we've analyzed it for 2 of the specimens, 1 female and 1 male. Of course, we have the data for all the specimens. We just haven't completed the work yet. There's still a bit of a way to go on this. But I wanted to show you some early results just because we're excited about it. And we're excited about the fact that we have this computational model and this experimental model that we can use to analyze many other things. So, to summarize, reverse arthroplasty is an optimization problem. You can move it inferior, you can move it superior. We haven't really spoken about that much, but we could analyze that now with our modeling. You can move it medially and you can move it laterally. If we move the glenoid center of rotation medially, it reduces the range of motion because of notching and other factors. But it increases the moment arm of the deltoid and therefore reduces the deltoid force. The deltoid doesn't have to work quite so hard. If you lateralize the glenosphere, then you can significantly increase the range of motion. you will also be loading the fixation of that glenosphere quite heavily. And so there may be loosening problems and failure of the glenosphere. But you also reduce the moment arm of the deltoid. And as you reduce the moment arm of the deltoid force has to go up to have the same torque to lift the arm up. So there is an optimization there. And then the further optimization is whether or not an acromioplasty does anything beneficial. I don't think we can say that there is a range of motion change. There's potentially reduction in the moment arm of the deltoid, which might increase the deltoid force. And should this not make it worse? But of course, the acromion is not just bending in one direction, it's bending in a second direction. And it's this out of plane bending that we think is influenced significantly by this work, and we can now analyze that. And as I finish, I thought I would just say that with this research that we can do some other interesting things. So one of our specimens had ossocromiale, this sort of loose acromion, where the fusion hadn't occurred at the growth plate along the acromion. And we found that the presence of this ossocromiale had a protective effect on the scapular spine, so reducing the strain on the scapular spine. And then when we fixed it, and we did this physically in the lab, but we also did this computationally, then this strain increased and maybe would be more likely to have a fatigue failure or fracture. But of course, ossocromiale does result in an acromion that actually moves quite a lot, and so there is the potential for impingement that we also were able to see. So as I close, I want to thank Andra for her brilliant work, Ulrich, my engineering colleague, and Peter and Toby, my clinical colleagues, who've done a great job in supporting this work. Thank you very much.
Thank you very much to all of the speakers in this section. Some really great talks. I was going to start with a question, Joaquin, for you. You spoke about when we're using the short stem humeral components, that we can sometimes fall into this trap of having them in varus or valgus malalignment, which has then implications potentially for the stability of our reverse shoulder arthroplasty construct. What are your tips to avoid that varus or valgus malalignment when you're preparing the humerus and inserting your component?
That's a great question, Ruth, and similar to what Dr. Alta mentioned for stemless, I think it can affect both a short stem and a stemless because we don't have the rhythm of the diaphysis. So what I try to do is, number one, pay attention to my planning so that I already anticipate using CT scan planning, where is it that I want my cut to be. I think for stemless and short stems, the cut, for the most part, dictates your alignment. That's why I mentioned in the video that I like to use an IM cutting guide. And also, even if you're using a shorter stem, sometimes it's wise to have a longer broach so that you can get at least the alignment of your metaphysis with the canal. If you have any questions, I think it's important to get x-rays because malalignment, I think, will have a detrimental effect on reverse, like you mentioned, for notching and instability, but also in anatomic if then you don't have the geometry of the humeral head reconstructed properly.
So you mean to get intraoperative fluoroscopy if you're having any kind of doubts about your prep or your
if you have any questions, but most of the times that is not necessary. If you pay attention to your CT scan, use some types of reference for cuts, and then use a longer broach, typically you get by.
Thank you. So I have a question initially for Anthony, but then others can perhaps chip in. This is more of a sort of general conceptual type question. One of the main reasons for developing this relationship and collaboration between SECEC and ISG was to bridge the gap between the sort of surgical clinical side of things and biomechanics. So perhaps Anthony, if you want to start, kind of how best do you think as the biomechanics community can we best serve the surgeons and the clinical side and then vice versa? So how can we sort of facilitate that bridging of that gap between these two fields?
Martin, I think that's a good question. So obviously the first thing that I tell any of my PhDs is that they should get in the clinic regularly, weekly, rub shoulders with the clinicians the whole time so that they're able to speak their language. And that's as a result of them having more time than the clinicians. And I think it's appropriate that they do so. I think the second thing is to recognize that we are influenced even maybe purists like ourselves who might sit in a lab or behind a computer a long time, we're influenced by those clinicians that we rub shoulders with, and that we need to have a broader mindset than just those individuals that we work with. And so it's important that we attempt to keep up with the literature, that we have a much wider collaboration than single clinicians. That's very important, although we recognize the strength of clinical leadership that might actually drive the big new ideas. Because as we all know in biomechanics and in the clinical domain, groupthink definitely drives people into a certain direction, and sometimes we need some big creative thinking to jump us out of that. So that's why I value this. I really appreciate it. I think it's fantastic that we're spending the evening here together. I haven't yet started on my whiskey, but I will do soon, and I'll toast you all.
Great, thanks, Anthony. Yeah, absolutely. I think it's. I think we can all be guilty of sometimes being in our own little silos. So, strictly say collaborating with people outside who we wouldn't normally collaborate with, it helps to build that discussion and knowledge transfer. Would anyone else like to come in on that point at all, on that question?
Can I add something?
Absolutely.
Yeah, I think it's from one side what Anthony was saying as well, that you need the clinical input to not go into a direction of biomechanical engineering which is completely not clinically relevant, so that you're doing wonderful, nice things, but we in the clinic we cannot do anything with. But it's also the other side. It needs to be cross-pollination, because you sometimes have wonderful, brilliant ideas that we as in this case shoulder surgeons did not think of. So don't only be there to facilitate the surgeons, also encourage them to listen to your new ideas, and because that probably will give the cross-pollination and come to brilliant ideas which we can clinically all have benefits from. So that's why I wanted to add, if you can still hear me.
Great.
Jack, you wanted to come in there? I see a hand raised.
Yes, I have a question, from Anthony's talk about the ossicruminale, and I wanted to ask it to Joaquin, Tjarco, and Puneet. How much of stress fractures do you see, and do you warn your patients with ossicruminale or big os if they are having a reverse shoulder replacement about any implication that can have?
I can go first. So for me, there is three different situations. One is the patient with the classic os acromiale.
Yeah.
So in those patients, I actually do not modify anything and don't try to fix the os acromiale. There was a paper by Jill Walsh that showed that patients seem to do reasonably well. And we have a paper, first author is William A. Binder, that showed that there wasn't a problem. A different and common situation is the patient that presents before reverse with a fracture of the spine before reverse. I've only seen that 5 times, always in rheumatoid patients.
Okay.
And in those, I have fixed the spine before doing the reverse. And then third is the patient that already has the reverse and has a fracture. And those, I think, we're seeing them in a rate of 1 to 2%. And I have become more aggressive at fixing them if they are more medial. I'm interested in the opinion of other surgeons or biomechanic experts in the call.
Jagwant, if I might go next. I completely agree with all those thoughts. I'll just add one more scenario, which is more common than the ossicruminale. Ossicruminale I'll treat like any other reverse, but you sometimes see patients with advanced cuff arthropathy where the acromion is completely eroded and fragmented. And I think what we tend to do as clinicians, we tend to assess if the deltoid trapezial fascia is intact. If the deltoid is functioning, and if you can see that is working well, the outcomes are going to be very similar to the ones where your acromion is intact. So you obviously warn them that the deltoid function may not be as high, but actually intervening for that can cause disruption of the deltoid trapezial fascia and disruption of the deltoid force. So sometimes it's one of those examples of less is more. That's my thought.
Yeah, I can. What I learned actually tonight is because in the beginning I thought ossicruminale. Oh, then the strength of the deltoid will be less. So you need to fix that. That's what I was taught in the beginning as well during my end of my residency and my fellowships. And then probably referring to the same paper as Joaquin was saying, found out that basically the clinical result is not different if there's either an osteochromiale or non-osteochromiale. The clinical outcome doesn't matter. So I'm not fixing any osteochromiale anymore. And I thought actually it was interesting to learn from you, Anthony. In this case, you're actually showing that it sort of can be protective to not get any spinal fractures, which you nicely explained how this could work. And I agree with Joaquin as well, that if it's more a spine fracture before you put it in a reverse, I think that's a different animal, as the Americans like to call it, because that's different pathology. So I agree that you first then need to fix the scapular fracture and then put in the reverse. So I think we all agree.
Thank
Yeah.
you.
I think
The other thing I'd say, sorry.
Go ahead, Puneet.
Oh, sorry. I was just going to say the scapular spine fractures. I think it's good. I completely agree that it's better to fix them early, and they're not easy to heal. You could fix them, and you could go back in and scan them, and they don't heal. The problem is the deltoid is pulling them away all the time. So the tip we've learned and burnt our fingers over the years is to do orthogonal plating. So to use two plates, one on the top and one on the side. And that makes the construct better. And the second tip is, if you're fixing them, to leave them in a position of slight under reduction. So you're not trying to restore anatomy, because a lot of times you have a little bit of a bone loss. If you leave the scapular spine injuries a little bit under reduced, and that actually helps them heal. So I don't know if that's been the experience of the other panel members, but I found it really hard to get them to heal. So these two things have helped us.
I think that's a really interesting concept that the clinicians will respond to, but I certainly will want to look into why you would under-reduce and what the mechanical effect of that would be. So that's an interesting one. Thanks for that.
Yeah, a few patients coming your way.
Yeah, I think those are good tips. I think, we often see those patients with osteochromiale, when you do the reverse, it will tilt down a little bit afterwards, and it seems to make absolutely no difference clinically. It doesn't impinge on anything, it doesn't bother anything. While it might look funny on an x-ray and make us think there should be some biomechanical effect, there just doesn't seem to be in the clinical reality. And I found it fascinating in Anthony's talk that, we tend to worry when we see that thinned out acromion in those cuffed arthropathy patients, that it looks so fragile and fragmented, and maybe they're at higher risk of problems with scapular spine fractures, acromial fractures. Maybe they're at a higher risk of an acromial fracture, but clinically those don't seem to be a problem. But it turns out that actually maybe that's protective, because they've sort of done their own acromioplasty before we ever met them. And that's something that I think is fascinating from the work they're doing at Imperial. So thank you, Anthony, for showing us that.
Yeah, can I ask another question about that? Because Anthony, you were saying if the osteochromiale is more tilted down, and then you were saying that can cause impingement. That's probably in your model which you were having, and then you were doing passive range of motion, and then you can have impingement. But I like to doubt that if that's really happening in the practice, because what the prosthesis can do, people with a reverse most of the time cannot use the active range of motion glenohumerally actively by themselves. So I'm doubting if they really get into that position from actively to create impingement, but it does create impingement if you move the shoulder passively. Have you any comments on that?
I think that was a supposition on my part, clearly, and I think that's something we need to test properly. So I think you're probably right. We need to investigate that further. But we're definitely having this, as Ruth said, the acromion definitely does tilt down significantly when you have osteochromiale. That's clear, and it changes the load distribution through to the scapular spine. That we're quite confident is protective of spinal fractures.
Anthony, have we looked at the CA ligament and, excising it or keeping it intact has any role in it?
We haven't in this model yet, but it's something we could easily look at, of course. Yeah.
I think we could probably spend all night talking about all of this scapular
More,
spine.
more research ideas. Thank you. Talk to me separately.
It bothers us all so much when a patient comes in because it's such a pain to try to get it to sort out. We do have one question before we move on to the next part of the webinar. I know we're borrowing a little bit of time from the next section, but we have one question from the audience, from Ravi Kumar Varadarajan. So the issue about the main reasons for revision for reverse, that on registries and long-term studies, these seem to be instability and glenoid loosening. I wonder, you know, that plus, I guess, in some other experiences, maybe infection, but do we think that instability and glenoid loosening are still the major reasons? Have we minimized some of these problems because of better implants, techniques? And so I suppose what he's asking is, in the past 5 years, you know, have we seen changes in the modes of failure of reverse? So if maybe the panelists can share their experience, starting with Puneet, you know, do you think that the failure modes are still glenoid loosening, instability, or what are our biggest failures in the reverse?
Yeah, thanks, Ruth. Yeah, it's a great question, actually. I think instability we've reduced massively over the last 10 to 15 years. I remember reading for my exams, and they're talking about the risk of complications after reverse is around 40%. And I've highlighted that I went back and read that book again. It was 15 years ago. And I can't believe that is true anymore. None of us would have that kind of a complication rate. And one of the biggest problems we were seeing was instability at the time. I think we brought it right down to a very, very low level. And I think that's to do with the design and the understanding of the biomechanics. So I think instability is low. If you look at the NJR, the first 2 years, the reverses do worse than the anatomicals. And I think that's to do with the instability and periprosthetic fractures. But when you look at 10, 11 years out on the registry data, the reverses start to do better than the anatomical. And I think the mode of failure, again, used to be notching and glenoid loosening. Again, we've overcome that by implant positioning, lower, building up the glenoid offset. And I think with the 135 trend on the humeral stem side, I think that will reduce even further, because the survivorship in the current data set, it goes back to this when we started collecting data. So we don't have the, you know, the hip and knee survivorship per, you know, as per years, where they can produce enough that data that way. So I think we're down to a very low level on both those points. I think the periprosthetic fracture is an issue. That's the biggest issue around the reverses, in my opinion.
Yeah, I think I can agree with you, Puneet. I think what we're doing is finding a way to have the prosthetic construct more stable, and with the 145 and 135 less needing to distalize. So I think there's also less deltoid fatigue, which was also a thing we were worrying of. So I think we're in the last 10, 15 years, we got better understanding this implant. And I think the periprosthetic fractures can be very challenging, as I showed you in my talk. So if we find the right balance, we all need to use a stemless reverse, but I'm not haven't found the right clue for everyone yet.
I agree to Tjarco, you know. The short stem is definitely helpful and prevents, you know, the long stems are a sitting duck, you know, people fall down and they have periprosthetic fractures.
Great. Well, thanks so much. I think I've had great discussions after some great talks, and we should probably hand over to the next section of the webinar.
I'll introduce the first speaker, which will be Professor Philipp Moroder. He's a multi-awarded researcher and orthopedic surgeon from Switzerland, also an active member of SECEC. And he and his team did some excellent research on the role of posture and scapular position related to the range of motion in reverse shoulder arthroplasty. And he hopefully will show some of his papers from digital simulation to translation to patient results. I'm looking forward. The floor is yours.
Thank you very much for the introduction, and thanks to SECEC and the ISB for inviting me to this new format. I love the opportunity to discuss with members of other professions on our common goal, which is to improve the outcome of our patients. And so without further ado, I would like to share the slides of my talk, and I hope you can see them well. Before I start talking about scapulothoracic orientation and kinematics in shoulder arthroplasty, I would like to point out a relevant conflict of interest. Currently, if we're discussing shoulder arthroplasty, our focus is quite limited to the glenohumeral joint, and we are kind of missing the big picture, because when we plan, when we implant, and when we follow up our patients, we only see the glenohumeral joint and we don't look beyond. A couple of years ago, we introduced the distinguishment between different posture types amongst our patient population. We have patients where we implant a reverse anatomical total shoulder arthroplasty that are very upright with retracted scapula. And then we have patients who are very kyphotic and have protected scapula with drooping, anterior tilt, and internal rotation. Now, does this really exist in clinical practice? This is some pictures of gentlemen of about the same age, and you can clearly see the differences in posture and scapulothoracic orientation. And if we now take a CT scan of these gentlemen, you can actually see how amazingly horizontal a scapula can sit in a patient who is kyphotic, and how straight, upward the scapula sits in a patient of a type A posture. So we did some simulation studies, virtual simulation studies, where we took CT scans of patients. We had virtual RTSAs implanted, different configurations, everything that you can imagine, over 3,000 different configurations. And we then measured the scapulothoracic orientation of this patient and separated the groups into 3 different posture types. And then what we saw in the simulated range of motion is that depending on the type of scapulothoracic orientation or posture type, we have a significant difference in the simulated range of motion. Now let's look into one of the parameters a little bit more close in order to make this concept a little bit easier to understand. If we, for example, look at the retrotorsion of the humeral component, and we take a patient with a posture type C, we see that if we implant a humeral component with 0 degree of retrotorsion, we get less simulated range of motion than if we implant it with, for example, 40 degree of retrotorsion. Now, why could this be the case? If we take some examples, we have a patient on the left with a posture type A, and on the right with a posture type C, and in the middle a posture type B. If the scapula has an internal rotation of 30 degrees, in theory, the humeral component would need to have 30 degrees of retrotorsion in order to have a balanced opposition of the components at 0 degree of rotation of the forearm, which makes a lot of sense, right? Obviously, I don't advocate for implanting reverses with 50 degree of retrotorsion in a patient with posture type C, because we obviously have to account for a certain resting internal rotation of humans, which is around 30 or maybe 20 degrees. So in my clinical practice, at least for now, what I do is, if I have a patient with a very upright sitting scapula, posture type A, I go for a little bit less of retrotorsion of about 10 degrees. And while I have a patient with a posture type C, more scapular internal rotation, I tend to give a little bit more humeral component retrotorsion around 30 degrees. A clinical example. If you look at this gentleman with a posture type C with a severe scapular internal rotation due to kyphosis, and you now implant a humeral component with 0 degree of retrotortion, you can see in this illustration and also in the virtual simulations that you will face early impingement or notching at the lateral border of the scapula, already neutral rotation of the arm. So you don't even need to externally rotate, and your humeral component will already touch the scapula and create notching. Now, if you use a humeral component retrotorsion that is close to scapular internal rotation, obviously you get a more balanced opposition of the components. This is a revision arthroplasty case with some exchangeable trials where I was able to simulate 0 degree of retrotorsion in a posture type C. And what you can see is this gapping in the front of the prosthesis due to early notching posterior inferiorly of the humeral component with the lateral border of the scapula. So whenever you see this anterior gapping, maybe consider a little bit more retrotorsion to the humeral component. But it's not only about rotation. If you look at this gentleman, and now we ask this gentleman not to rotate, but to elevate their arms, which would look like this. This is what we want to obtain in clinical practice, right? We want to have this famous 180 degrees of flexion and abduction that nobody of us is truly getting. But if we are honest, this is quite unfair. Because if we ask a posture type C patient to raise the arms to the roof, I always say it's like you laying down on your stomach and then raising your arms to the roof. It's not going to happen because the scapula is sitting so horizontally in space. So what is depicted here is a more fair comparison of a true elevation that these patients are able to achieve at best. Some clinical examples again. This is a 73-year-old Swiss lady, and she has unilateral shoulder problems. The other shoulder is perfectly fine, never had any problems. On the left, where she had problems, I implanted a reverse total shoulder arthroplasty. And if we look at the outcome, I was quite happy with the elevation that she was able to obtain. And not surprisingly, on her contralateral side, where she has no problems at all, she also has a very nice elevation. Now let's look at the 87-year-old Swiss woman, and she has a different body posture. She got a reverse on the right shoulder as well because of problems. And on the left shoulder, she claims to never had any problems at all. She's perfect on the left. Now let's look at the outcome of the reverse total shoulder arthroplasty that I implanted on the right shoulder. And honestly, what is it? Is it maybe 100 degrees? Depends on how generous you are with yourself in your clinical assessment, but it's certainly not anywhere close to 160 or even 180 degrees. And now if we look at her left shoulder, where the patient herself claims to never have had any problems in her life and has a fully functional shoulder, that's about what she gets on the other side. So it's also a function of the scapulothoracic orientation and likely also kinematic capabilities of the scapulothoracic articulation. Now we looked also at some clinical data in order to verify these concepts that are more theoretical. So we followed up 681 patients for 2 years after reverse total shoulder arthroplasty. We took clinical examinations and X-ray follow-ups, and then we distinguished patients with different posture types, A, B, and C. And this cohort of 681 patients with reverse includes a variety of surgeons, different implant styles, different companies. Generally, it's a mix all across over different years. And what we see is that regardless which surgeons with which style of implantation implants whatever company, we get a significantly worse outcome for patients with worse posture. And this is true for outcome scores like the SPADI. It's also true for pain. But it's also true for range of motion, as for example, abduction and flexion. Also, there was some trend, a clear trend for external and internal rotation, even though not reaching significant. But there have been some follow-up studies from other institutions that redid the same study essentially, and they found the same outcomes, even finding relevant differences in rotation. What about complications? There was no statistically significant difference, even though you might argue there's a trend for more complications in posture type C patients in terms of glenoid loosening and acromion spine fractures. However, I would like to point out a severe confounder, which might be osteoporosis, which leads to kyphotic fractures of the thoracic spine, and as such could be a confounder leading also to more risk for scapulospine fractures and glenoid loosening due to bad bone quality. Now, what about simulated range of motion? If we currently simulate range of motion, this is true for whatever company you're using out there, it is quite interesting to see that you get this data of what the expected range of motion is after implantation of a reverse total shoulder arthroplasty. Now, what is interesting is if you take a patient with posture type C, like I did on this example, so I took the CT scan of a patient looking like this on the upper left-hand side, and I uploaded it to different company softwares, and what you can see is that all of a sudden, miraculously, the scapula sits straight in space and the humerus is parallel oriented to the scapula. So somehow these softwares all take the scapula for being straight in space and the humerus being aligned with it. So what we are currently simulating is a virtual posture type 0 that is non-existent, at least to my knowledge, in reality. So we have a malposition of the scapula at the beginning of these simulations. And since the humerus is aligned with the scapula, we also have a malposition at the start of the simulations of the humerus, which can be quite severe. And then, obviously, what follows is also a problem with the kinematic planes, because all of a sudden, if we simulate an abduction, we get more of a scaption. And if we simulate a flexion, we get something weird like a cross-body adduction. So we have a large systematic error. And you could argue that while simulated range of motion might be precise, it's definitely not accurate, or how I like to call it, it's precisely inaccurate because we have a large systematic mistake. We try to quantify this with a study that we recently published, where we took 10 randomly selected cases of 3D models of patients going for reverse total shoulder arthroplasty, fit them into a statistical shape model, and we did virtual RTSA implantation with 6 different surgeons. And then we simulated range of motion with and without adjustment for posture. And what we found is a significant, a large difference between simulated range of motion in all planes of motion. And if you look at the data, you can find an average difference of 50 degrees, for example, for flexion. And I remind you, this is on a scale from maybe 0 to 160. We see differences of 24 to 47 for extension. Maybe the scale goes out to 60 or 70 degrees. External rotation is just the same, 27 to 50 degrees. So the systematic error is on average so large that it really jeopardizes the entire concept of scapulothoracic or of simulated range of motion without adjustment for scapulothoracic orientation. If we look at clinical outcomes, there is some studies that have looked at the difference between simulated outcome and clinical outcome. And what they found is more flexion, less external rotation, more abduction, more high external rotation, and less high internal rotation. And quite interestingly, this is also the trend that we observe with our posture adjustment simulation. So I'm not claiming this is the truth, but it's likely going in the right direction if you account for scapulothoracic resting orientation for simulated range of motion. Now, why is it not the real truth just yet? Because obviously we also have to respect kinematics. This is a gentleman that has calf arthropathy on both sides. So you would expect that both sides have the same poor or good function depending on whether he's compensating or not. However, what you can see is this gentleman can perfectly elevate or almost perfectly elevate on the right, while he cannot elevate at all on the left shoulder, despite both shoulders looking quite similar. Why is this the case? Because this gentleman has accessory nerve palsy and trapezius paralysis, and this is why his scapular motion is impeded, and this is also why he cannot compensate on the left shoulder. So kinematics of the scapula seem to be important, and there's a variety of studies that we can look at that have used different methods of detecting scapulothoracic motion. One of the methods is single plane fluoroscopy, as used by David Walker, who showed us that the scapulohumeral rhythm is different if you implant a reverse total shoulder arthroplasty compared to a native state. If you have a reverse, then more scapular motion compensates for what you are missing on the glenohumeral side. So I'm not saying that our reverses are functional arthrodesis, but they certainly do not allow us for the same glenohumeral motion as the native shoulder does. And the scapula, luckily, makes up for it, at least partly. There's some interesting studies also coming out from Italy. The group of Giuseppe Porcellini used inertial sensors to see what the effect of reverse total shoulder arthroplasty on scapulothoracic motion is. And what he found is that the scapula anticipates the elevation motion of the arm in flexion and abduction and retracts and posteriorly tilts in order to facilitate the elevation of the arm. Now, there's also other interesting studies with even more sophisticated methodology to detect very precisely scapulothoracic motion. This is coming from Heath Henninger, a great study, who looked at differences in glenohumeral and also scapulohumeral motion based on weighted scaption and not weighted scaption. And what he found is that while some patients were able to have a nice glenohumeral abduction, with also a little bit of scapulothoracic abduction, when they put some weights in the hands of these patients, actually the glenohumeral motion got less, while the scapulothoracic motion got a little bit more, meaning it tried to compensate and partly was able to do so, not completely, but at least the scapulothoracic motion seems to be our friend in reverse total shoulder arthroplasty. And some other interesting studies have shown that this is not constant in time. This can actually change. In this study, it was shown that from 6 to 12 months after the implantation of a reverse total shoulder arthroplasty, there's a difference in scapulohumeral rhythm, especially between the 90 and 120 degrees elevation. And actually, this seems to decrease, which means that the glenohumeral motion gets a little bit less over time, while the scapular motion seems to increasingly compensate for that. And there's a colleague of mine, Patrick Rice, with his team in Munich. He actually did a nice physio study, and I think we are also going to hear a little bit more in the next talk about the possibilities of whether we can influence this phenomenon. And he did a randomized controlled trial, which is quite nice, where he had patients 1 to 2 years after reverse total shoulder arthroplasty, where you would actually expect them to reach a plateau and not really change the clinical outcome. He randomized them to receive functional electrical stimulation by means of the so-called shoulder pacemaker. One group got the training with the pacemaker, and the other group got the same training with the pacemaker, also worn on the shoulders, but not turned on. And what he found when using this functional electrical stimulation, as shown here in these different images, you can also see how he trained one of the patients on the right-hand side. They got a reverse, and on the left-hand side, you can see how it's used even for athletic persons. You can see that these patients actually gained quite substantially, even though they were 1 year or 2 years after reverse total shoulder arthroplasty implantation. So they got an increase of 20% on the subjective shoulder value, 12 points on the constant score, and so on, while in the control group, where they did the same exercises, they did not have any statistically significant changes. Now, another interesting study coming from the group of Heath Henninger is about internal rotation, because I believe that's one of the motion parameters that we really cannot predict after reverse total shoulder arthroplasty and quite often can be limited, is what effect does scapulothoracic orientation and kinematics have on internal rotation? And what he found is, or his group found, is that patients with high internal rotation are more close to what I would call a posture type A, very upright, retracted scapula, more upward rotation, and less negative tilt of the scapula. And what you can see on the upper right-hand side is how different the rotation and scapular motion is for patients with high internal rotation. Generally, they seem to have a more mobile scapula, which helps them to internally rotate better. So in conclusion, posture types and scapulothoracic orientation indeed have a significant effect not only in simulated but also in clinical range of motion after reverse total shoulder arthroplasty, and this is regardless of implant configuration. And therefore, posture types should be accounted for when planning and implanting a reverse total shoulder arthroplasty. Now, interestingly, glenohumeral kinematics may change to the verse over time, but also might be susceptible to training. And this is where our colleagues from the physiotherapy come in and might help us get the better outcome for our patients. Scapular kinematics luckily usually enhance or improve our range of motion, but in certain instances might also limit it. And potentially scapular kinematics may also be susceptible to training. And maybe we're going to hear more about this in the next talk. Thank you very much.
Thank you, Philipp. Great talk. Solon, if you may proceed.
So Professor Michener, user physiotherapist, is director of the Clinical Biomechanics and Orthopedic Outcomes Research Laboratory at the University of Southern California. The central theme of Professor Michener's funded research is to define optimal treatment pathways for patients with musculoskeletal shoulder disorders. So she will talk about scapular kinematics and physiotherapy.
Great. So describing these common scapulothoracic deficits that we might see and talk about, can we clinically identify these deficits that may be present in patients post-reverse in particular will be a big focus of my talk, and also what physiotherapy approaches might be helpful to remediate these deficits. So we see different impairments in patients with post-arthroscopy and predominantly, or arthroplasty, and predominantly that reverse I'll be focusing on today. And we see soft tissue tightness, maybe some thoracic impairments that are obviously present, as we saw earlier, even prior to surgery, and some motion deficits that I'll talk about first. So as we all know, the scapula has 3 rotations, that internal, external rotation, upward, downward rotation, and anterior-posterior tilt. We have a lot of focus on the upward and downward rotation. It's the largest amount of motion. When we look at some results from a pinning study that we did early in Philadelphia with colleagues Carduna, McClure, Sennett, and myself, we were trying to validate an external sensor set to look at scapular motion and thus implanted or drilled in these K-wires into the scapula to track direct scapular motion. From this, we got nice data to understand what's happening with the scapula. And as you can see along the x-axis, before I show you the cartoon graph of this data, that this was up to 140 degrees, because as we start to elevate, as you can imagine, some skin tugging on those bone pins. So just 140 degrees is what this represents. So we can see that the 2-to-1 ratio that's been commonly described was approximately demonstrated in that bone pinning understanding of how the scapula moves during upward rotation. When we look at posterior tilt and external rotation, we can see that not a lot of posterior tilt and external rotation occur early on in the motion, up to about 90 degrees, and then we start to see this posterior tilt external rotation occurring. And this, as noted in the top left, is during scapular plane elevation. It looks a bit different when we go into different planes, and just as a representation here for flexion, we can see that internal external rotation really stays more in that internally rotated position, and it bounces between internal external rotation as we go into flexion. So point taken that scapular motion can look different as we're attempting different planes of elevation of the humerus. This is a systematic review meta-analysis published in 2022 about what do we know about kinematic evaluation, in particular scapulohumeral rhythm after reverse total shoulder. And you can see here that there are 4 studies in this systematic review, and the number of participants is kind of low given that there are 4 studies, but there are 48 participants with a reverse total shoulder and 63 who are their healthy controls, asymptomatic shoulders predominantly on the opposite side of the patients who had a reverse. As you can see, and then the forest plot, all studies showed to varying degrees that there's an increase in scapular contribution during glenohumeral elevation, and in particular upward rotation. And so all 4 studies showed this common phenomena that there is a contribution greater from the scapula to achieve that overall arm elevation. If we look a little bit more in detail from some of their other data, you can see the scapulohumeral ratio is a bit smaller in those participants with reverse shoulder to the patients on the control group or the healthy quote unquote shoulder. And you can see up here in the forest plot, that difference was 1.16. So essentially, again, the contribution is coming more from the scapula in those who have a reverse total shoulder. I just put out this one graph from one of the studies, including the systematic review meta-analysis. It was only from 13 participants, but I thought it really depicted nicely. Over the x-axis is the humeral elevation angle. You can see this goes up to 120. And on the y-axis is scapular upward rotation. In the dashed line is the contralateral shoulder, assuming to be the healthy shoulder, and then the reverse total shoulder on the opposite side. And as you can see, in the reverse total shoulder population, that there is greater upward rotation across the entire phase of elevation. And in this particular graph, and that's not consistent across all studies, it shows a relative similar contribution of greater scapular upward rotation across the entire range of elevation. A study was just reviewed by Philipp in the prior presentation, showed that the scapulohumeral rhythm with this reverse total shoulder with these inertial units that were measured, and they looked at them at 1-year follow-up. And they looked at not just upward rotation, which was a nice contribution here, but also looked at posterior tilt and external rotation as well. As you can see on the graphs on the right, the pink is the reverse total shoulder, and the blue lines are the healthy side. As you can see, as they elevate, in the first graph up at the top, is there's greater posterior tilts occurring in the reverse total shoulder. There's greater upward rotation, as we consistently saw in the systematic review from prior, and there is also greater external rotation, or that retraction or protraction as they describe here on the label for the graph. You can see, interestingly enough, that retraction doesn't occur consistently throughout the range of motion. The next question I think was quite interesting, and understanding whether or not these motions change over the course of recovery. In this study in clinical biomechanics in 2023, this group looked at understanding over the course of care, do these patients improve? And actually outside the course of care as well, because this goes at 3, 6, and 18 months. What we can see is that upward rotation and posterior tilt improved, but it was still less than the other shoulder, the contralateral shoulder. We can see that upward rotation improved as well as posterior tilt improved. We can also see that humeral elevation improved as well, but again, as been pointed out nicely through all the presentations, they're not getting back to the magical 180 degrees. They're getting back to a bit over 100, about 110 degrees at that 18-month mark. And as pointed out before, the Spady score improves in these patients. This used the DASH score, and you can see with the DASH score, lower percentage is less disability, and they improved in their function as well. And DASH being both symptoms and function had some nice improvement in both. So what do we know? That the scapular upward rotation has a larger contribution, and some other studies have also shown that posterior tilt and external rotation as well, but scapular upward rotation is the most robust finding. So can we identify these visually? So patients come in, can we identify these upward rotation, posterior tilt, external rotation, or a combination visually to understand whether or not we want to identify these particular deficits? So in an observational clinical exam, we can ask people to do a lifting test and understand when they lift, and this is with weights in particular, can we identify some abnormal motion about the scapula? And this is in particular in flexion, but it can be done in abduction, scaption as well. So back in 2009, described a dyskinesis test. Can we visually look at this using some weights to understand, weights in their hand that is, to understand potential abnormalities of displacement of their infraangular medial border, that common winging that we may see, dysrhythmia, this lack of normal scapulohumeral rhythm during raising and lowering. Asking patients to do this 5 times, and do we see this abnormality 3 of the 5 times? And prior studies have looked and said, we want to classify each individual motion. Is there greater upward rotation? Is there greater posterior tilt? Is there greater external rotation, or vice versa? And that did not deem appropriate because it had limited reliability and poor validity that we can assess each individual motion visually. But classifying them either as abnormal or normal has good reliability and validity. So these might look like this. You can see on the right, that elevates a bit more. And then the bottom one on the left, you can see as they come down, the scapula falls down a bit quicker, has greater downward rotation on the left. 2 examples of dysrhythmia. This visual scapular dyskinesis test is looking for abnormal motion, not asymmetrical motion. That's because asymmetrical movement is normal. Shoulder pain, in a prior study in kinematic assessment, shoulder pain patients had 71 to 77% asymmetrical motion, and that was almost exactly the same as the healthy match control group. So asymmetry is not what we should be looking at in a visual exam, because asymmetry is normal, quote unquote, similar to that in a healthy group. We see also that people have dyskinesis both in this people with shoulder pain and people without. A study we did earlier, looking at a blinded examiner, examining patients with shoulder pain and looking at how their scapula moved, that we see during abduction and flexion that the scapular dyskinesis test was positive in a similar amount in both shoulder pain as compared to patients who are healthy match controls or patients without shoulder pain. So basically, no difference in prevalence between those with and without shoulder pain. So again, difficult to understand. We're not looking for asymmetry, and also, can we really say whether or not they have shoulder pain when we see this? So scapular deficits are present, but we don't know if they're a result of the total shoulder or something that was present prior, such as the thoracic posture that we saw earlier. They do improve over time postoperatively. When, though, is there still intervention needed to improve that scapular motion is unclear with a clinical exam. Symptom alteration tests may be helpful to assist in the control of scapular motion and see, does that change their pain or function, to understand, are there potential deficits that we visually see, but to understand their relevance to the individual patient, are they changing their pain or function? And this picture here is an example of a scapular cyst test, for example. So what do we know from the evidence? Looking at a clinical practice guideline I was involved with in 2023, the physical therapist management of glenoid humeral joint osteoarthritis, and then subsequently also arthroplasty was included in this. The question was, in patients post-operatively, does patient PT management result in improved outcomes, and what interventions can result in those improved outcomes? And not to a surprise, recommending, but it's really best practice because there was no clinical trials that showed, in the absence of high or moderate evidence, PT services can benefit patient-reported outcomes, but there's insufficient evidence in randomized clinical trials. So we need more research to understand what and should be done exactly, and when is physical therapy needed. I look forward to reading the randomized control trial that Philipp mentioned earlier. So what's the treatment focus? On pain, range of motion, and muscle function are the three things, with that scapular muscle control and stabilization and deltoid. And I'll leave you with this recent paper that just came out in 2024 in Journal of Shoulder and Elbow. They looked at 44 people with reverse total shoulder arthroplasty, 12 weeks post-RTSA, and understanding using EMG what activities in particular increased deltoid activity to the highest, what increased trapezius and serratus with respect to those scapular muscles we may want to target. And if I walk you through the graph, the deltoid, if I really want to target deltoid, this table slide exercise has low deltoid activity. The standing closed chain, meaning they're sliding their hand up the wall, has moderate activity. We really want to increase their deltoid activity the most, and they can tolerate this. This open chain, forward flexion, scaption, or overhead reach really had the highest EMG activity. If we're looking to highlight scapular muscle activity, this lower level table activity again is low for those, and then get into moderate and high for this closed chain and open chain. So moving across the continuum, they need to start in this lower position and then moving to higher positions with open or closed chain against the wall to increase those activity of the muscles we want to target. Thank you.
Great talk. Thank you so much, Professor Michener. Very nice to hear from you and from Philipp as well on scapula. So happy to proceed. Maybe one of the other panelists have questions for our speakers.
Laura, you mentioned obviously post-op, we don't necessarily know what happened, kind of was happening scapular kinematics wise pre-op. What's your kind of view, or what was the evidence around any pre-operative physical therapy or physiotherapy exercises to hopefully improve outcomes post-op?
There was very limited evidence in the clinical practice guideline that we found for efficacious or effectiveness with respect to delivering preoperative strengthening. I would assume, and this is just what we recommended in the guideline, that preoperative seems to be a good idea just to get the patient ready to be in best shape post, but limited evidence suggesting whether or not strengthening prior and range of motion improves outcomes post.
And I see one just sort of little follow-up question. So you mentioned the different components to exercises that physical therapist or physiotherapist might prescribe, mentioning sort of motor control. So with that in mind, obviously different approaches to different motor control exercises. So can you expand on that and kind of what you feel is the best sort of concept or approach regarding motor control type exercises?
I guess if we were looking at scapula, for example, and using that as understanding what we're trying to control, patients elevating their arm, and when we help them into upward rotation or controlling not going into so much upward rotation, and they achieved greater elevation or had less pain, then I would be focusing on having them concentrate on contracting that and really helping to elevate, and starting with a lower load to the arm So maybe I really would need to start in that gravity eliminated position on the table and then move into that support on the wall and then with an open chain.
So, Laurie, I have a question for you. What do you think about recovering thoracic spine mobility in rehabilitation to improve scapular mobility, in particular in upward rotation and posterior tilt? And the second question is also about rehabilitation. What do you think about using kinetic chain to improve activation of scapular muscles and to increase neuromotor coordination?
I'll take the second question first as it follows with the last question. There is evidence to suggest that incorporating the kinetic chain, i.e. incorporating trunk, lower extremity, one or both, can help to improve shoulder activation. So yes, I think that's a great idea, and that I didn't touch upon that with example, the exercise study that I reviewed, but evidence indicates that that definitely improves shoulder muscle activity. We saw in a study just looking at healthy controls, closed chain versus open chain, and controlling for the amount of weight they were lifting, but closed chain increases EMG activity, and closed chain tends to involve much more kinetic chain, increases activity as well. Thoracic spine posture. I'd love to hear Philipp's thought about this. I'm not convinced that we can change posture. I think posture is what it is, and maybe you can get people out of the habits of being in a less, more flex posture, but your ability to actually change and statically improve their posture, I'm not sure that we have any evidence to suggest that we can actually do that. Philipp, your thoughts?
I unfortunately completely agree with you, Laurie. I don't think there is any easy way to obtain improvement in posture. You might obtain a little bit of improvement temporarily, but static posture is what it is, and it actually gets worse with time. And quite interestingly, we are born with a fixed degree of humeral torsion, for example. It's set at early age during adolescence. That's defined. But then at the same time, our scapular internal rotation is worse and worse and worse and worse over time. In some patients, more so than in others. And then we have this mismatch between scapulothoracic orientation and body axis and the humeral torsion, for example. And this is one of the problems we are facing. And I don't really think we can change it. But kinematics might be susceptible to training, as you suggested. And I think more so postoperatively, because we have to account for the pain factor. These patients are operated because they have an issue, and most of the time it's pain. And so we cannot easily train them because obviously they say, no, but doctor, I have pain. I cannot do these exercises, right? So I would love to send all my patients to pre-op training, because they might improve muscle strength, and they also might increase the loads on the deltoid, and by doing so, the loads on the acromion and spine, and maybe already build up some bony strength to anticipate the feat that is to come to bear the strains of a reverse total shoulder arthroplasty. In theory, that sounds very nice. In practice, I have not been able to do this on a consistent basis with my patients, to be honest.
Okay. Great question. We've got one from the audience, if I may ask them to you, Philipp, from Professor Henniger, which you referred to as well. And he is asking about posture in a supine CT scan. Have you analyzed the patients to determine if that classification changes during upright postures? And if so, how frequently?
Yeah, thank you very much for this question, Heath. I'm actually a fan of Heath. He is doing excellent research in this particular field, and I'm always reading his manuscripts. And he actually also shared some of his data openly, so I encourage you to look into that a little bit more. So to your question, Heath, we have been recently looking into this, comparing supine CT scan data with upright ultrasound-based 3D tracking of the scapula, which is a quite surprisingly nice technique to do it, non-invasive, but obviously it's not as precise as CT scan. But what we saw is not a consistent change in scapula from, let's say, quite upright in the supine position to a more kyphotic position once the patient stands up. It's quite surprising that it doesn't really show a clear trend in one direction, at least on the preliminary data that I've seen, but we are lacking the final analysis so far. To my knowledge, there's one publication out there coming from Japan that looked at supine versus standing CT scans, and the differences they found, they were not as large as I expected, but more to come on this topic.
Thank you. Great talks. I have a question for Philipp. Philipp, really fascinating work on scapulothoracic posture and the influence on reverse. So the question is conceptual, and you may have done some research on that. When we're performing a reverse shoulder arthroplasty in someone with a severe deformity, the scapula will not only be tilted forwards, but also tilted laterally. And in this three-dimensional space, do you see an influence of the neck shaft angle on the impingement-free range of motion? Also, if there is a choice in correcting the lateralization in a reverse for someone with a severe thoracic deformity, would you prefer to correct it on the glenoid side or on the humeral side? So two questions, but perhaps related to each other.
So we have been looking into this recently as well, and I can only share some simulation results, which may or may not translate to clinical reality. So please take everything with a grain of salt that I'm saying. It's not yet validated in reality, but at least in the simulations, it looks like if you have a patient with a very bad kyphosis, and I get now some weird CT scans from all over the world with very bad internally rotated scapula, you will be amazed how much they can be internally rotated. And in these cases, what I suggest, at least based on simulations, is on the humeral side, give a little bit more retrotorsion and a steeper neck shaft angle. And on the glenoid side, what might be a factor is to move the glenoid more lateral and also a little bit more posteriorly in order to avoid the lateral border of the scapula. It's quite interesting to see that in a patient with a very kyphotic and horizontally orientated scapula, all of a sudden in the simulation, the liner starts to impinge with the posterior glenoid rim behind the glenosphere if it's not large enough. It's quite interesting to see, while in patients with a very upright posture, like this young sporty gentleman with a B2 osteoarthritis where you might do a reverse or not, they tend to actually impinge more with the coracoid and the anterior superior acromion and limit internal rotation. So there is some concepts where you may be able to improve, but again, this is simulations. This is not real life just yet.
Very good. Thank you.
Great talk, Philipp and Laurie. I mean, do you think that the current planning softwares which are used every time now will be incorporating the scapulothoracic orientation in the near future?
In my opinion, this is quite easy to implement actually, and I hope that in the future we will see this implemented in all simulated range of motion that we get from our preoperative planning softwares. But then again, it's also not going to be able to predict range of motion because soft tissue comes into play, scapular kinematics comes into play, many different factors that are yet to be explored. But we are going one step further, right? One step at a time.
Great. We are already exceeded the time, but thank you to everyone for all the contributions and the great talks we had this evening. So I would like to invite everyone for our next webinar, which is on the 12th of March. And this is on managing bone loss management in severe shoulder arthroplasty by Marcella Sucumano. And also we invite everyone to our next Congress in September, and that's in Rotterdam. Tjarco is organizing that. So we'll love to see everyone there. And the registrations are open, and there is special discount for the SECEC members.